Hello everybody. Welcome to the second lecture of linear transformation. In the last lecture, what we studied, let us recall. So we take VF and WF to be two vector spaces over a same field F, and we say that a map T from V to W. Here, for the sake of simplicity, we are writing V to be V instead of VF and W to be WF. Because there is no case of confusion here, the target field is obviously F. So from now onwards, we shall write V instead of VF and W instead of WF. So this map T from V to W is said to be a linear transformation if T of x plus y is equal to T of x plus T of y. Here the two conditions are needed in the definition. The first one is T of sum is equal to sum of the T values for every xy in V, and the second condition is T of alpha x should be equal to alpha into Tx for every alpha in F and x in V. This is the definition of a linear transformation. The next theorem gives us an alternative definition of T, where instead of two conditions, we have just a one condition that requires to be a function between two vector spaces over a same field to be a linear transformation. So if is T from V to W, it is a linear transformation. Here we have already assumed that this V and W, they are vector spaces over a same field F. If and only if. Instead of two conditions, we have only one condition. What is that condition? T of alpha x plus beta y is equal to alpha tx plus beta ty for every alpha beta in F and xy in V. This we already proved in our last lecture. So in this particular lecture, we shall prove some of the important properties of linear transformation. So what is the theorem? Suppose T from V to W is a linear transformation, then the following holds. What are the properties? Number one is T of 0 is 0 dash. The 0 on the left side represents the 0 vector of V, and 0 dash on right side, it represents the 0 vector of W. Number two, T of minus x is equal to minus T of x, where x is in V. Third is, basically the third property is a direct consequence of second property. V. And fourth one is T of Px is equal to P of Tx for every P to be integer and x is a vector. So let us prove them one by one. So first is, consider T of 0. We can write it as T of 0 plus 0, because we can write 0 plus 0 equal to 0. Apply the definition of T to the right side, we get this is t of 0 plus t of 0. Now each term, basically t of 0 is the only term that is in the expression. So all these terms, they are members of w. So if we add 0 of w, which is 0 dash, to one of the to any term, basically we are adding it to the left side, it makes no difference. Now all the four terms, they are members of w, and since we know that w is an abelian group being a vector space, so since we know that both left cancellation law and right cancellation law holds good in case of in case of a general group, so by applying left cancellation law here, that means we can cancel t of 0 to the both sides. We get 0 dash is equal to t of 0, that is t of 0 is equal to 0 dash, which is property number first. That means a linear transformation always maps 0 to 0. Let me come to property number 2. For x in V arbitrary, what is t of x plus minus x? This is t of 0 because x plus minus x is the additive inverse of x. So the sum will be equal to 0. And we have just proved that this is equal to 0 dash. And on the left side, by applying the property of linear transformation, we get, now the sum of these two elements, these are the two elements of w, is equal to 0 of the w. This is possible only when these two elements are additive inverses of each other. So by the definition, t of minus x is nothing but t of minus t of x. This is property number 2. Now come to property number 3, where we take x and y in V arbitrarily. Then t of x minus y, basically x minus y is the representation of x plus minus y. Applying the definition of t, this is equal to t of x plus t of minus y by the property number 1, which is given in the definition of linear transformation. So this is equal to t of x, and what we proved in property number 2, just we have proved that t of minus y is nothing but minus t of y. So this representation is nothing but t of x minus t of y. Therefore, we can say that t of x minus y is equal to t of x minus t of y for every x, y in V. Now let's come to property number 4, the final property of this theorem. Here we have to prove that t of px is equal to p of tx for every p belongs to z and x belongs to V. So we take p an integer and x in V arbitrary. We shall prove that t of px is equal to p of tx. We shall divide the proof in 3 parts. In first part, we shall take p equal to 0. In second part, we shall assume p to be a positive integer. And finally, we shall prove that the same result is true when p is a negative integer. So collectively, we can say that for any p to be an integer, t of px is equal to p of tx. So in the case first, we assume p to be equal to 0. Then take left side, t of px, this will become t of 0x, this is t of 0, and this is 0 dash by part 1, and p of tx, this is 0, tx. This is 0 dash. Since the two quantities are same, so we can say that the result is true. That means t of px is equal to p of tx for p equal to 0. Now we shall prove the same result when p is a positive integer, and we can prove it by using one of the most famous result of number theory, that is the principle of mathematical induction. So case 2, when p belongs to set of natural numbers, that means p is a positive integer. So here in step first, we shall prove the result for p equal to 1. So it's obvious, when p equal to 1, let me write it, when p is equal to 1, t of px is equal to t of 1x is equal to t of x, and the term on the other side, p of tx, is 1 of 1 into tx, which is again tx. We can see that these two quantities are same, so the result is true for p equal to 1. That means t of px is equal to p of tx for p equal to 1. Now in the second step, which is uh, nothing to do much, basically that is the assumption step. We assume that the result is true for some fixed positive integer. Let us assume that the result is true for p equal to k. Step second, suppose the result is true for p equal to k, that is t of kx is k of tx, where k is a positive integer. And the main step to be done is step 3, where we have to show that the same result is true for the next positive integer which we have taken in assumption step, that is step second. That means we have to prove that t of k plus 1 x is equal to k plus 1 tx. So let us take left side of the expression. This is t of k plus 1x. This is nothing but kx plus x. Applying the definition of t, this becomes t of kx plus t of x. Now the first term of the sum, t of kx, this will become k of tx by virtue of step number 2 of principle of mathematical induction, where we assume that the result is true for p equal to k. So this becomes k plus 1 tx. Thus, the principle of mathematical induction is completed. So we can say that t of px is equal to p of tx for every p belongs to set of natural numbers, or you can say set of positive integers. Now in case 1 and case 2, we have proved that the result is true for positive integers as well as for 0. So all we need to show that it is also true for negative integers. So for the negative integers, we shall use the case of positive integers. So case third is when p is a negative integer. Suppose we take p to be minus m, and m has to be set of natural numbers. Then t of px is equal to t of minus mx. This is equal to t of minus mx. This is one of the most fundamental property. Now this is equal to minus t of mx. This is the property number 2 of the same theorem. t where we proved that t of minus x is minus t of x. Now forget everything. This term t of mx, where here m is a positive integer, and we have just proved that the result is true when p happens to be a positive integer. So we can write it. This is, we can say that this is equal to m times tx, because we have proved that this result is true when p is positive. So here instead of p we are taking m, and m is a natural number. So this becomes minus mtx, and minus m is again p. So t of px is equal to p of tx when p happens to be negative integer. So combining all the three cases, you can say that t of px is equal to p of tx for every p in z and x in. So that's all for today's lecture. In the next lecture, we shall prove some more important properties of a linear transformation. Till then, thank you very much.